the quality of service implementation techniques. Now that you have learned about traffic characteristics, queuing algorithms, and QoS models, it is time to learn about QoS implementation techniques. Let's start with packet loss. Packet loss is usually the result of congestions on an interface. Most applications that use TCP experience a slowdown because TCP automatically adjusts to network congestions. Dropped TCP segment cause TCP sessions to reduce their window sizes. Some applications do not use TCP and cannot handle drops or fragile flows. The following approaches can prevent drops in sensitive applications. Increase link capacity to ease or prevent congestion. Guarantee enough bandwidth and increase buffer space to accommodate burst of traffic from fragile flows, or WFQ. CBWFQ and LLQ can guarantee bandwidth and provide prioritized forwarding to drop-sensitive applications. Drop lower priority packets before congestion occurs. Cisco IOS QoS provides queuing mechanisms such as weighted random early detection, or WRED, that start dropping lower priority packets before congestions occurs. QoS tools. There are three categories of QoS tools. As described in the table below, the first one is classification and marking tools, congestion avoidance tools, and congestion management tools. Tools for implementing QoS. The first one is the classification and making tools. This is a session or flows are analyzed to determine what the traffic class they belong to. And when the traffic class is determined, the packets are marked. The second one is the congestion avoidance tools. In these tools, traffic classes are allotted portions of network resources as defined by QoS policy. And QoS policy also identifies how some traffic may be selectively dropped, delayed, or remarked to avoid congestion. The primary congestion avoidance tools is WRED and is used to regulate TCP data traffic in a bandwidth efficient manner before tail drop caused by queue overflows occur. And the last one is the congestion management tools. When traffic exceeds available network resources, traffic is queued to await availability of resources. Common Cisco IOS-based congestion management tools include CBWFQ and LLQ algorithms under these tools. Refer to the figure to help understand the sequence of how these tools are used when QoS is applied to packet flows. The first one is the QoS sequence. Take note that the classification and marking can be done in ingress or ingress, whereas other QoS actions such as queuing and shaping are usually done on egress. As shown in the figure, egress packets or gray squares are classified and their respective IP header is marked colored squares. To avoid congestion, packets are then allocated resources based on defined policies Packets are then queued and forwarded out of the egress interface based on their defined QoS shaping and policy. Now, classification and marking. Before a packet can have QoS policy applied to it, the packet has to be classified. Classification and marking allow us to identify or mark types of packets. Classification determines the class of traffic to which packets or frames belongs. Only after traffic is marked can policies be applied to it. How a packet is classified depends on the QoS implementation. Methods of classifying traffic flows at layer 2 and 3 include using interfaces, ACLs, and class maps. Traffic can also be classified at layer 4 to 7 using network-based applications recognition or NBAR. Take note that the NBAR is a classification and protocol discovery features of Cisco IOS software that work with QoS features. NVAR is out of scope on this course. Marking means that we are adding a value to the packet header. Devices receiving the packet look at the marked field to see if it is matches a defined policy. Marking should be done as close to the source device as possible. This establishes the trust boundary. How traffic is marked usually depend on the technology. The table in the figure describes some of the marking field used in various technologies. The decision of whether to mark traffic at layer 2 or 3 or both is not trivial and should made after consideration of the following points. Number 1, layer 2 marking of frames can be performed for non-IP traffic. Layer 2 marking of frames is the only QoS options available for which switches that are not IP aware. Layer 3 marking will carry the QoS information end-to-end. The traffic marking for QoS using the following table, the QoS tools. For layer 2, Ethernet 802.1q, 802.1p. Marking field is a class of service or COS. Width in bits is 3. 802.11 for Wi-Fi. This is in layer 2. Wi-Fi traffic identifier or TID. And the bytes is 3 or bits is 3. And for MPLS, layer 2, experimental for marking field, and width in bits is 3 also. And the last one is IPv4 and IPv4 and IPv6. This is IP preference of precedence or IPP with 3 bits. And we have the IPv4, IPv6, layer 3, differentiated services code or point. Differentiated services code point or DSCP with the bits of 6. The 802.1q standard also includes the QoS prioritization scheme known as IEEE 802.1p. The 802.1p standard uses the first 3 bits in the tag control information or TCI field, known as the priority or PRI field. This 3-bit field identifies the class of service or COS. Marking. 3 bits means that a layer 2 Ethernet frame can be marked with one of the 8 levels of priority. That is from value 0 to 7 as displayed in the figure. So the 3 bits means that a layer 2 Ethernet frame can be marked with one of the following 8 levels of priority, values 0, 1 to 7. For example, for best effort data, the cost binary value is 000 and the cost value is COS value is 0. Medium priority is 001, cost value is 1, and so on, so forth. And then the marking at layer 3. Marking at layer 3, IPv4 and IPv6 specify an 8-bit field in their packets and packet headers to mark packets. As you can see in the figure, both IPv4 and IPv6 support an 8-bit field for marking. The type of service or TOS field for IPv4 and the traffic class field for IPv6. Type of service and traffic class field. The type of service and classes traffic class field, the type of service and traffic class field carry the packet marking as assigned by the QoS classification tools. The field is then referred to by receiving devices which forward the packets based on the approaches assigned QoS policy. The figure displays the content of the 8-bit field that is in RFC 791, the original IP standard specified in the IP precedence or IPP field to be used for QoS markings. However, in practice, these 3 bits did not provide enough granularity to implement QoS. The RFC 2474 supersedes RFC 791 and redefines the TOS field by renaming and extending the IPP field. The new field, as shown in the figure, has 6-bit allocated for QoS called the Differentiated Service Code or DSCP field. These 6 bits offer a maximum of 64 possible classes of service, and the remaining 2 IP explicit congestion notification or ECN bits can be used by ECN aware routers to mark packets instead of dropping them. The ECN marking informs downstream routers that there is a congestion in the packet flow. Now the DCP values. The 64 DSCP values are organized into 3 categories. Number 1 is the best effort or BE. This is the default for all IP packets. The DSCP value is 0. The per hop behavior is normal routing. When a router experiences congestion, these packets will be dropped. No QoS plan is implemented. The second one is Expedited Forwarding or EF. Under the RFC 3246 defines EF as the DSCP decimal value 46 with binary 101110. The first 3 bits, 10101, map directly to the layer 2 cost value 5 used for voice traffic. At layer 3, Cisco recommends that EF only be used to mark voice packets. And then the last one is the Assured Forwarding or AF. Under the RFC 2597 defines Assured Forwarding to use the 5 most significant DSCP bits to indicate queues and drop preference. The definition of AF is illustrated in the figure. Assured forwarding values are shown in the figure. The AFXY formula is specified as follows. The first three most significant bits are used to designate the class. Class 4 is the best queue and class 1 is the worst queue. The fourth and fifth most significant bits are used to designate the drop preference. The sixth most significant bit is set to 0. For example, in AF32 belongs to class 3, binary 011, and has a medium drop preference binary 10. The full DSCP value is 28 because you include the sixth 0 bit. So binary 0111100. Next is the class selector bits. Because the first three bits, most significant bits of the DSCP field indicates the class. 3 bits are also called the class selectors or CS bits. These 3 bits map directly to the 3 bits of the QoS field and the IPP field to maintain compatibility with 802.1p and RFC 791, as you can see in the figure. The table in the figure shows how the QoS value map to the class selectors and the corresponding DSCP 6-bit value. The same table can be used to map IPP values to the class selectors. The trust boundaries. Where should marking occur? Traffic should be classified and marked as close to its source as technically and administratively feasible. This defines the trust boundary as shown in the figure. Trusted endpoints have the capabilities and intelligence to mark application traffic to the appropriate layer 2 QoS and layer 3 DSCP values. For example of a trusted endpoint include IP phone, wireless access points, video conferencing gateways and systems, IP conferencing stations, and more. Secure endpoints can have traffic marked at the layer 2 switch. Traffic can also be marked at layer 3 switch or routers. Remarking traffic, for example, remarking QoS values to IP precedence or DSCP value is typically necessary. The last one is the congestion avoidance. Congestion management includes queuing and scheduling methods where excess traffic is buffered or queued and sometimes dropped while it waits to be sent out an egress interface. Congestion avoidance rules or avoidance tools are simpler. They monitor network traffic loads in an effort to anticipate and avoid congestion at common network and internetwork bottlenecks before congestion becomes a problem. These tools can monitor the average depth of queue as represented in the figure, when the queue is below the minimum threshold, there are no drops. As the queue fills up the maximum threshold, a small percentage of packets are dropped. When the maximum threshold is passed, all packets are dropped. In the congestion avoidance, the figure, the Q full, maximum threshold, minimum threshold, and Q empty. If this is a Q full drops, maximum threshold, percent drops, and the minimum threshold will be no drops. Some congestion avoidance techniques provide preferential treatment for which the packets will get dropped. For example, the Cisco IOS QoS includes weighted random early detection as possible congestion avoidance solution. The WRED algorithms allows for congestion avoidance on network interfaces by providing a buffer management and allowing TCP traffic to decrease or throttle back before buffers are exhausted. Using WRED helps avoid tail drops and maximize network use and TCP-based application performance. There is no congestion avoidance for user datagram protocol or UTP-based traffic, such as voice traffic. In case of UTP-based traffic, methods such as queuing and compression techniques help to reduce and even prevent UDP packet loss. So that's all for this video. For the next video, we're going to continue the other topics in Chapter 9. The shaping and policing. The shaping and policing. The traffic shaping and traffic policing are two mechanisms provided by Cisco IOS QoS software to prevent congestion. The traffic shaping retains excess packets in queue and then schedules the excess for later transmission over increment of time. Traffic shaping results in a smooth packet output rate. Shaping is an output concept. Packets going out on the interface get queued and can be shaped. In contrast, policing is applied to an inbound traffic on an interface. Policing is applied to inbound traffic on an interface. Policing is commonly implemented by service providers to enforce a contracted customer information rate or CIR. However, the service provider may also allow bursting over the CIR if the service provider's network is not currently experiencing congestions. The quality of service policies must consider the full path for source to destination. A few guidelines that help ensure the best experience for end users include the following: enabling queuing at every device in path between source and destination, classify and mark traffic as close to the source as possible, and shape and police traffic flows as close to their source as possible. That's all for Module 9. So let's prepare for module practice and quiz.